Hello, my name is Dakota Brinklow.
I'm Dustin Evers.
I'm Chris Holdiner,
And I'm Anthony O'Hara.
and we're Group 9, and our project was on the statistical analysis of bridge rectifier ICs under high ambient temperatures.
Hey everybody, an outline of our project that we completed for our presentation was to inspect the thermal limitations of a bridge rectifier circuit and in comparison to the standard operating temperatures stated or claimed by the manufacturer on the data sheet. To do this, we performed some tests on 9 ICs randomly selected. We ordered them from DigiKey, and we put them under full electrical load of approximately 75 watts. Started off with a room temperature basis at that full load, and then we increased the ambient temperature over time, making recordings of the current, the voltage, and the temperature of the chip using a thermal probe throughout the testing procedure. We then performed a statistical analysis on the data that we recorded for the testing to confirm the manufacturer's data sheet and whether their rated temperature limitations were on spec or if they were well conservative or out of bounds from what our test data showed. And then we use that data to also calculate various probabilities on maximum temperature ranges and probabilities of failure for specific temperatures, and we put them into a histogram that we'll show you in a few minutes.
Thank you.
Hey everybody, this is going to be our process and procedure for testing the thermal threshold of an IC rectifier chip. What we have here is a variac set to a certain AC voltage. We're going to use an oscilloscope to measure that voltage and view the waveform. And we have our IC hooked up with a thermal probe attached to the top using thermal tape, a load resistor external to the oven itself, so it's not impacted by the high temperatures also. We're only looking at the high temperature effect of the rectifier itself. And we're going to take temperature, current, and voltage measurements as the temperature is increased during the test. We're going to start off with a full a full electrical threshold of the IC chip based on the spec sheet, which we have pre-set up here. So we have a maximum voltage and current, so it's at full load, and let this warm up to an operating temperature. Our oven's also warming up. Okay, and then we're going to increase the temperature of the oven gradually throughout the experiment and find the point monitoring the voltage, current, and temperature where the IC chip actually fails. So I'm going to go ahead and put it in the oven now. Well, it's not resting on anything in the oven, it's just suspended in the air. And the chips are rated for 150 degrees Celsius operating temperature max at full rated load. And right now our oven is at about 200, and we're going to continue to increase that. The oven's at about 300 degrees Fahrenheit, which is approximately 150 degrees Celsius. So we're at the thermal threshold now. It shouldn't be long. Monitor the voltage here. One thing the oscilloscope will do for us is it'll give us an early indication of degradation of the IC chip, and we can see early signs of thermal failure based on distortions that we'll see in the rectified output. So we're kind of adjusting our input voltage. I'm seeing some distortions now, and that's it. We just had failure. It was about 200 and
86 degrees Celsius.
So our first test was to check if the datasheet temperature versus current ratings were actually accurate. So we decided to take our sample of 9 chips and connect them up to the datasheet rated load of 75 watts. And then we decided to record the steady state temperatures of each chip. And then we plotted that on a graph as shown here. The blue line shows the datasheet temperature versus current characteristic. Note that the current X is the X-axis and temperature is on the Y-axis. And then the orange dots are the data that we had collected from our chips. You'll note that all of the data that we have collected falls below the datasheet line. So basically this proved that the datasheet spec for temperature versus current was conservative. But this is to be expected because the manufacturer wants to provide a high level of confidence in their product. So we also looked at the deviation of each point from the line from the datasheet. So we had a maximum deviation below the line of 57.53 degrees and a minimum deviation of 7.07 degrees. So as you can see, a lot of these values varied depending on the chip. Some of that's due to some measurement error, but the idea was to take a sample of 9 measurements so that we could get a good idea of the temperature specs of these chips. So we were very pleased with this data, and because of that we decided to proceed with a detailed failure analysis of this IC. So during our test, we hooked up an oscilloscope to the output of the rectifier IC to observe the change in voltage as we increase the temperature. As you can see in this capture, you see the full wave rectified output of the rectifier IC. And this was helpful so we could view when the rectifier IC failed. We had a situation where the resistor that we used for our load had failed, and this was important because it showed us that the rectifier chip was still operational when the load had failed. In the case of the rectifier chip failing, we would see distortions in this waveform, and eventually the rectified output would disappear, indicating that the chip had failed. So this was a useful tool in determining the failure point of rectifier ICs.
Using our gathered data from the testing of the 9 samples chips we used, we took it to MATLAB to find some general chip failure data, including some different sources of errors we found. As you can see in the graph, we've got the chip test numbers on the x-axis and the temperatures of failure on the y-axis. The mean temperature of failure was a 269.78 degrees Celsius. The standard deviation was 13.95 degrees Celsius. The minimum failure value was 241 degrees Celsius, and the maximum was 285 degrees Celsius. We took in an array of different averages of where the chips failed and then plotted it on this graph. Certain significant sources of error that we felt were noticeably enough to talk about was the thermocouple placement. The thermocouple was taped, and depending on the different locations of where the thermocouple was taped on, we could have lost or gained a couple of degrees in the testing. The temperature meter error, just like an average multimeter, could have a couple degrees of error when we were doing our general measurements. And the most significant one we felt was the speed at which the data was taken. After we had the experiment ready and we put it in the oven, which was already hot, we found that measuring the voltage, current, and the temperature all at the same time as it was decreasing very fast was a very hard task to do. So we felt that that was the most significant source of error of the error. Using our data in MATLAB, we made different histograms. With temperature on the x-axis and number of failures being on the y-axis, we tried every fit in MATLAB and found that we the Weibel was the best one, but we'd like to compare to. So on the left, we've got the normal fit, which we saw the line wasn't very accurate or significant enough. And on the right, we have our Weibel, which we thought was a good indicator to try to find probabilities.
Okay, so here we have the failure percentage at given temperatures, and this table of data is off of the Weibel fit line. And first note that 200 degrees Celsius, the percent failure rate is 0.0089, and on the data sheet it is specified that the degrees Celsius of the cutoff range would be 150 of operation. Going down the list of percent failure, we have a big jump between 250, 260, 270, and 280. This is where we found most of our chips to fail in that range, and anything that goes above 290, 300 is 100% failure. Okay, now we're going to look at the effects of the IC failure at experimental temperature threshold. So what happened right before the chip failed is we had a large surge current going through the variac, which actually tripped the 4 amp breaker. Some effects of the failures of the IC chips as seen. This is probably the best picture of one right here. There's a nice crack right down the middle, as you can see there. So that was a big physical change to the chip, which caused the output waveform to distort and then go to 0 as soon as it cracked. Another physical change we have is you can see the pins on this IC chip right here are nice and shiny and silver, and these ones are a purplish blue. So we came to the conclusion that the pins actually oxidized because they were taking in so much power at a single time. Because of all that power being delivered to the load too, we actually had a load resistor get red hot and crack and bust apart, which was actually, like we concluded, that actually had some fluctuation a little bit on our data, but not significant enough to sway it one way or another. We also had another effect, and that was we had a couple IC chips, actually I think all of them were above the threshold of melting solder. So we actually had to use crimps to crimp onto the IC chips instead of using solder. So in an application of using this chip in a high temperature area, you'd either need a higher temperature solder threshold or you'd have to clip on actually without using solder. Wrapping this all together, using the data we gathered, we found that the IC chips can actually go over the threshold of the data sheet of 150 degrees Celsius. We actually found that they can go up to about, our mean temperature was like 269, which is significantly higher than the data sheet value. We use this data and we determine the probability at which they will fail at under these extreme conditions. And application would be the IC can be exposed to higher temperatures than the data sheet specifies. So we could technically use this in a high temperature setting rather than a lower temperature setting.